In this video, we're going to talk about continuity of a function. We're going to do this in a variety of different ways. So first of all, we start with the idea of continuous at a point. Okay, so this means it's continuous at a specific x value. So first we think of this intuitively. Okay, so if a function is continuous, we say a function is continuous at a point if we can draw the function near the x value, without lifting our pen or pencil if you prefer. So if that's not possible, then we say it's discontinuous at that point. Okay, so when would it not be possible? Okay, there might be a hole, there could be a jump in the graph at that point, there could be an asymptote. Okay, there's lots of ways where we might not be able to do this. In those cases, we would say discontinuous. More precisely, though, we say that a function f is continuous at x equals c if the following three things are satisfied. So first of all, we need the y value, f of c, to exist. Okay, so this guarantees that there is a point at x equals c. Okay, so the y value exists. We also want the limit as x approaches c of our function to exist. So what that says is that the y value approached exists and is the same on both sides in order for the limit to exist. So as we approach c from the left and from the right, we approach the same y value. And in fact, we want this y value to be f of c. Okay, so the limit of as x goes to c of f of x should in fact be equal to f of c. Okay, so this is kind of the most important bit. It kind of encapsulates the other two things as well. Okay, so as long as this exists, okay, then if the limit is equal to that, then obviously the limit exists as well. So if it's not continuous at x equals c, at least one of these conditions is not satisfied, which we would say it's discontinuous at c. So I've given you here 4 examples that are all discontinuous at x equals 2. So we're going to see which of the 3 things break down in each. Okay, possibly there's more that break down. Okay, so this one I'm going to call A. So we're going to go in this order. Okay, so for A, here's our graph of f of x. So first of all, is 2 in the domain? I don't see a point at 2 because there's a hole. Okay, so f of 2 does not exist. Okay, so that breaks number 1, which therefore breaks number 3. Okay, the limit does exist actually. So the limit as we approach 2 of our function is actually 3. Okay, but it's not equal. So the limit, I'm going to use shorthand here. So the limit does not equal f of 2 because f of 2 doesn't even exist. Okay, so here 1 and therefore 3 fail. Okay, now in part B, okay, now we do have a point. So f of 2 is actually 3. Okay, so 1 is true. The limit as we approach 2, though, does not exist. Okay, because from different sides, they go to different numbers. So the left-hand limit goes to 1. Okay, so as we approach from this side, we're approaching this hole, which is at y equals 1. And as we come to the right, we're approaching the point here at 3. So because 1 and 3 are different, the limit doesn't exist, and therefore it cannot equal to 3. Okay, so here we have 2 and 3 fail. Okay, now what about part C here? Oops. So we have an asymptote, okay, at x equals 2. So 2 is not in the domain. So again, f of 2 doesn't exist. Now for the limit, as we approach 2, okay, on both sides, the y values are getting very large. Okay, so they're both going to positive infinity, so we would write that this limit equals positive infinity. But remember, we have to, positive infinity is not a thing, so that doesn't exist either, and therefore they're not equal. Okay, so here all of the rules fail. 1, 2, and 3 fail. I mean, technically, the limit, yeah, they all fail. Okay, for D, there is a point. Okay, so, well, maybe I'll do it over here. So f of 2 is equal to 0. Okay, there is a point, so 1 satisfied. The limit as we go to 2 of f of x also exists, because as we approach 2 from both sides, okay, we're approaching the y value -3. Okay, but the limit as we go to 2 of f of x, like I just said, is -3, which is not the same as f of 2. So here, it's only number 3 that fails. Okay, now in each case, if I try to draw the graph, notice once I get to 2, I have to lift up before I can continue. Okay, for this one, there's a jump, so I really have to lift up. In part C, there's an asymptote, so again, I have to lift my pen. And even in D, I have to lift my pen, and I'd have to try and dot that thing as well. So I can't draw the graph around x equals 2 without lifting my pen in any of these 4 scenarios. Okay, so there's lots of ways where you could not be continuous at a point. Now, notice that we could redefine the point at x equals 2, redefine or in fact define. Okay, so if it wasn't in the domain, at x equals 2 to make them continuous. So in particular, I'm looking at parts A and parts D. Okay, so where the limit exists. Okay, so these ones are where the limit as we went to 2 existed. Okay, but maybe it wasn't the right point. It wasn't at the right point. Okay, so we could redefine where that point is. Okay, so in A, we could define f of 2 to be equal to 3. Okay, so if we just sort of plug this hole in a sense, because there's no point there. So if we put a point there, then it would be continuous at 2. Okay, so that's kind of an easy fix. Okay, so then f of x is continuous at x equals 2. Okay, and in D, we could redefine. Okay, so it does have a point. Okay, so f of 2 was at 0. Okay, but we should redefine it to be at -3. So what I want to do is just grab this point and move it here so it plugs that hole. Okay, then f of x would be continuous at x equals 2. Okay, so those are sort of easy-ish fixes. For the other ones, in order to make it continuous, well, I'd have to get rid of this asymptote, which I can't do. And then even for B, I'd have to like shift an entire part of the graph down, like to match. Okay, so that's like kind of a big change. Just plugging a hole seems like a small change comparatively. So we talk about these discontinuities in a different way. So when the function can be made continuous at a point by defining or redefining the value at this point, we call the discontinuity a removable discontinuity. Okay, if the discontinuity has a jump or an asymptote, okay, non-removable. Okay, so what you want to remember, if it's removable, okay, it means that the limit as we approach that value exists. Okay, so then that means that you have a hole of some kind. Okay, if it's non-removable, these are the ones where the limit does not exist. Okay, so they usually have a jump or a asymptote. Okay, so there's two types of discontinuity. Now, we can also talk about continuity on an interval. Okay, so the function f is continuous on the open interval. So notice I'm using round brackets here, so I'm not including the endpoints, either a or b. So it's continuous on the interval if it is continuous at every point within the interval. So continuous for all x values. Okay, maybe I shouldn't say for all. Maybe I'll say at all. Continuous at all x values, where x is between a and b, but not including. Okay, so if it's continuous everywhere in between, then it's continuous on that interval. Now, if you want to include the endpoints, so you want to talk about continuity on a closed interval, so notice the square brackets, then we need to talk about continuity at these endpoints. But because we're focused in on this interval, we don't really care if the limit sort of exists on the other side. That doesn't matter. Okay, so we need to be a bit more specific about how we approach a and b. So if it's continuous on the closed interval, okay, it has to be continuous on the open interval. So it's continuous on the interval from a to b, so not including the endpoints. And then we want to make sure that it is continuous. Okay, I'm going to put it in quotation. So on the right of a, okay, and it is continuous on the left of b. So these are the only sides that matter in our interval. Okay, so what that means, so from the from the right, I want the limit as I approach a from the right of my function. I want the point to be in the right place, so I want that to equal f of a. And as I go from the left of b, okay, I need the limit to equal f of b. Okay, so maybe I'll draw you a couple pictures here. So continuous on the interval, so maybe here's a, here's b. Okay, so maybe I have something like this. Okay, so this would be continuous on the open interval a to b, because I can draw all these points that are inside without lifting my pen, so they're all continuous. But the endpoint limits, so as I approach a from this side, I go to this hole, not this point. Okay, as I approach b from this side, I go to this hole, not where the point is. Okay, so it's only continuous on the open interval. If I had something, oops, I'm still in blue. If I had something like, okay, so still a and b, I'm going to do something very similar. Okay, so something like this. This one is continuous on the interval, okay, including a, but not including b. So why can I include a but not b? So as I approach a on the left, notice that I'm approaching f of a. So that's where the point is. So it doesn't matter that the limit on the left is going to this point. Doesn't matter. The point is here and I'm approaching on this side. Now if I approach b from the left, I'm going to this hole. The point is down here. Okay, so on this interval, we would be continuous at a but not at b. Okay, so that's why I do square bracket here, round bracket here. Now, just to mention, obviously the graph is also continuous on these other intervals, okay? But we're just talking about between a and b. So just be aware of that. Okay, let's try an example. So we have the function f of x is the square root of 4 minus x squared. Okay, and we want to know on which intervals is this function continuous. So first of all, to be continuous at a point, we need the point to exist. So we want to think about the domain of this function. So we need 4 minus x squared to be bigger than or equal to 0 in order for it to be in the domain. So if we can think about factoring this. This is a difference of squares. So 2 minus x, 2 plus x should be bigger than or equal to 0. So solving these quadratic inequalities can be challenging. So it equals 0. Maybe I'll write this in blue. Okay, so this equals 0 when x is 2 or negative 2. So that means that the only places where it can switch from positive to negative or negative to positive is at these two x values. So one method to solve this is to think about a table. Okay, so like a number line. Okay, and plot your negative 2 and your 2, and then just test a point in each interval. Okay, so let's say I test negative 3. So when I'm less than negative 2, this function is always exists or doesn't exist. Okay, so that means that this part, so the inside part, is always negative or always positive. So if I plug in negative 3 into here, either or, so you can plug it into this, the factored form, or the non-factored form. Okay, I'm going to have 2 minus negative 3 times 2 minus 3, or plus negative 3. So this is 5 times minus 1, so minus 5. Okay, so it's negative here. If I do something in the middle, let's say 0 is the easiest. Okay, so this is 2 minus 0 times 2 plus 0. So that's going to be 4. Okay, so that means it's positive in this interval. And if I try 3, it's going to be 2 minus 3, 2 plus 3. So again, I get minus 1 times 5. So minus 5. So it's negative here. So that means that we have to be in this interval in order for this to be positive. Okay, so that means that, maybe I'll write this out. So 4 minus x squared is bigger than 0 when x is between negative 2 and 2. Okay, that's the only spot. So that means that our domain is the interval from negative 2 to 2, including the endpoints. Now it's useful to actually draw this graph. You should maybe have an idea of what it looks like, but you might not. It's more recognizable if I write it, so this is a y. If I square both sides and then move the x over, it's x squared plus y squared equals 4. Okay, this is the equation for a circle centered at the origin with radius square root of 4. So when we take the positive square root, it means that we're the top half of the circle. Okay, so what this actually looks like, is like that. Okay, where this is negative 2 and 2, and this point is actually 0, 2 as well, because it's a circle. So think about, where would the limit not exist? Oops. So if but when I'm between negative 2 and 2, the y values exist. Okay, so that's number 1 is valid. So now I want to think number 2 on my continuity checklist is, where does the limit exist? Remember, when we're computing limits, if we can plug in the value, then our limit exists. So for all of these values, we can plug it in. So you're going to get the same answer. So because of the limit laws that we know, the limit as x goes to c, let's say, of our function f of x equals f of c, okay, for all x with in between negative 2 and 2. Okay, so because we can plug them in, nothing bad's going to happen. So we get the right number. So this means that it's continuous on the open interval from negative 2 to 2. We should check the endpoints. because these limits are a bit weird because it only exists on one side, technically we should do it separately. So I'm going to approach -2 from the right. Okay, but we can actually just still plug them in. So this is square root 4 minus x squared. It's going to go to 0. Okay, and also, which is f of -2, by the way. And also the limit as we go to 2 from the left is also 0. Which is also f of 2. Okay, so this one is actually continuous on its entire domain. So from on the domain, the interval from -2, including -2, all the way to 2. Okay, but technically we should check those endpoints separately. So I just looked at the right and left limits. That makes sense. Now, we don't actually have to do all of this work because there's lots of functions that we know are continuous. And then there's ways to put them together to get other continuous functions. So here's a list of a bunch of functions with their intervals in which they're continuous. Okay, so the first one is a polynomial function. So I've written out what that looks like. So like a constant times x to the n plus a constant x to the n minus 1, etc. Okay, these are continuous everywhere, always. Okay, so from -infinity all the way to infinity. They're always continuous. Rational functions, so if you have a polynomial divided by a polynomial, these are also continuous everywhere except where the denominator is 0. So continuous for all x where q of x does not equal 0. Okay, so as long as the bottom isn't 0, these things are continuous at every other point. Now if you have a root function, I wrote it as a linear function inside, but it doesn't matter. They're also continuous everywhere in their domain. Okay, so continuous for all x where the function inside, so ax plus b, is at least 0. The exponential functions, which we haven't talked about fully, but they're a constant to the power x, so the x is in the exponent now. These are continuous everywhere. Okay, so for all x from -infinity to infinity. When you have a log function, they're continuous as everywhere in their domain. So that's from 0 to infinity, so not including 0. The trig functions are a little bit more complicated. Okay, sine and cos are continuous everywhere. So this is -infinity to infinity. Tan, however, we can write as sine over cos. Okay, so it is actually continuous everywhere that cosine x is not equal to 0. Okay, so as long as the bottom's not 0, again, it's continuous. Now, we can also take continuous functions and put them together. So suppose that f of x and g of x are both continuous at c. Then we know f of x plus or minus g of x is also continuous at x equals c. F of x times g of x is going to be continuous at x equals c. F of x over g of x is going to be continuous at c as long as g of c is not 0. Okay, so that would be bad. We can never divide by 0. And also, we can also compose them. So f of g of x is also continuous, but here I actually need, as long as f of x is continuous. So instead of at c, it needs to be continuous at g of c. Okay, but as long as it is, then that composition is also continuous at c. So one more example. Okay. Okay, so what is the largest interval for which this function is continuous? So what we want to think, so this is a piecewise function. Okay, so when I'm less than -1, I have to use this piece. And when I'm bigger than -1, I use this other piece. Okay, now first of all, we know that 2x plus 3 and 1 minus x squared are continuous everywhere. Okay, so -infinity to infinity, since they're polynomials. Okay, so they're one of the ones that we just talked about. Okay, so they're polynomials, so they're continuous everywhere. So that means, maybe I'll write this below. Okay, so f of x, our function, is continuous on the intervals they're defined. Okay, so on the interval -infinity to -1, and the interval from -1 to infinity. Okay, but neither of them I include -1. Because a weird thing happens there, and I want to make sure, I need to check that point specifically. Okay, so we need to check continuity at x equals -1. Okay, but it's continuous everywhere else. So what we want to know is it continuous also at -1? So what I want to do is check my three conditions. So what would be f of -1? Well, when I plug in -1, I'm in this interval because I'm equal to -1. So I'm going to use this formula. So it's going to be 1 minus -1 squared. So that's 1 minus 1, so 0. So I do have a point. Okay, f of -1 exists. Now to do the limit, I actually have to look at the left and right hand limits. Okay, so let's do the right hand limit first. So when I'm approaching from the right, it means that I'm slightly bigger than -1. So I'm going to use the formula 1 minus x squared. Because this is a polynomial, this limit is the function evaluated at -1. So it's going to be 1 minus -1 squared, which is 0. Now, when I approach from the left, okay, now I'm slightly less than -1. So I have to use the formula 2x plus 3, which means that it's going to be 2 times -1 plus 3. So that's -2 plus 3, that's 1. So because these are different, the limit as we go to -1 of f of x does not exist. Okay, so we would say f of x is continuous on the interval. So when we have multiple intervals that don't overlap, we use like a capital U symbol to put them together. So from -infinity to -1, and then we use that symbol, and then from -1 to infinity. Okay, so this says all x with x not equal -1. Okay, but it wanted interval notation, so we should use the interval notation. Now these are round brackets, not square brackets. That one looks a bit square. Okay. And if you draw this function, you'll see that they don't meet up at the -1. Okay, so the graphs go to different spots, which is why, so we have a jump in the graph, okay, which is why the limit doesn't exist there. So the function's not continuous there.